In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 14. As the topic is of continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with complicacy of star-star connected Y-phase transformer. There are 4 different types of connections employed for 3-phase transformers, and out of which star-star connection is the most economical type of connection for small current and high voltage transformers. In star-star connection, primary as well as secondary winding voltages in any phase are 120-degree apart from the voltages in any other phase. Each primary and secondary winding is connected to a neutral point, which may or may not be brought out of the tank for external connection. However, based on requirement, the neutral may or may not be grounded. For 3-phase transformer, each primary winding is magnetically linked to one secondary winding through a common core limb. Through the exciting voltages are of sinusoidal in nature, but the transformer magnetizing currents are never be purely sinusoidal, as due to have the presence of significant quantities of odd harmonic components in the magnetic circuits. Again, I repeat, though the exciting voltages are of sinusoidal in nature, but the transformer magnetizing current are never be purely sinusoidal, as due to have the presence of significant quantities of odd harmonic components in the magnetizing currents. See the diagram. This is the voltage cycle of a 3-phase system, labeled to 0 to 360 degree along the time axis. Now, advantages of star-star connection. As for star-star connection, line current equals to phase current, and phase voltage equals to line voltage by √3. Therefore, the voltage gets reduced in phase and subsequently reduces the number of turns per phase, causing a less stress on insulation. If the neutral end of a star-connected winding is grounded, then it is required to provide a reduced level of insulation at the neutral end of the winding. But in star-connected winding, where connection is across the phases, has to provide same grade of insulation throughout the winding. Again, I repeat, in delta-connected winding, where connection is across the phases, has to provide same grade of insulation throughout the winding. There is no phase angle displacement between primary and secondary voltages. This advantage has become evident when transformers are deployed in an interconnected systems of different voltage levels in a cascading manner. Star points on both sides make it possible to provide a neutral connection and suitable to use as for 3-phase 4-wire system. In 3-phase 4-wire system, the current flows through the neutral is a vector sum of the 3 line to neutral currents. Under balanced 3-phase linear currents, which are maintaining perfect sine waves, having each of the phase current 120-degree apart. Then at any instant, the vector sum of the three line to neutral currents is 0. Hence, under balanced condition, there will be no flow of current through neutral. Substations with interconnected system of different voltage level, star-star connected transformers would have been much more acceptable, where the secondary load is not comprised of non-sinusoidal loads. That is, all the time, more or less, load is perfectly sinusoidal. In fact, using star-star connected transformer for high voltage transmission system is much more economical because the voltage across the phase of each winding is a factor of 1.732 less than the voltage between the lines. Service would have become satisfactory only if the three-phase load is balanced. Any sort of unbalancing in load that would have to instigate for shifting the electrical neutral from its exact center to some other point, causing the line to neutral voltages unequal. But most of the system grid has always been connected with industrial load, which may have to compromise of unbalanced load like the furnace transformers or some sort of heavy duty rectifier and converter transformers, etc. As for industrial application, where the system is always been entertained with cyclic pattern of load and also simultaneously might have been encountered with a frequent surge of overcurrent and overvoltage caused by short circuits. So, therefore, the corresponding power grid has constantly been operated under very harsh condition because of handling significant amount of non-linear loads. Connected AC electrical loads are to be emphatically categorized as either linear or non-linear, depending on how the connected loads draw current from the mains, that is the transformer power supply waveform. Now see the chart. Linear loads can be classified as one, resistive load, that is electrical heaters, incandescents, light bulbs, or capacitive load. Capacitors usually found as part of the system or equipments, or inductive load, that is transformers, motors, or combination of some of them. With a linear time variant electrical load, the voltage and current waveforms are become sinusoidal, and the current drawn at any instant is proportional to the voltage. When a linear load is connected to the normal alternating current power system, the said load has to draw sinusoidal current at the same frequency as the voltage, though that current usually is not in phase with the voltage. With nonlinear load, the current is not proportional to the voltage. In case of nonlinear loading phenomenon, the current would have to fluctuate with the alternating load impedance, which indicates that the current as drawn by the load does not have the same waveform as the supply voltage. Such nonlinear loading would have to draw current in abrupt short pulses rather than in smooth sinusoidal wave. The current waveforms are thereby distorted by these short pulses, which in turn generates harmonics. Harmonics are the consequence of the effect of non-fundamental frequency components of a distorted power frequency waveform. Harmonic current components, as generated by any nonlinear load, flows from the load into the power system, are rather responsible for the degradation of the power system performance and reliability. Harmonics in the power system would have become much more susceptible for the malfunction of circuit breaker, large amount of neutral currents, skin effects, overheating of transformer, decrement in power factors, distortion in voltages, and extra losses in rotating machines. So, the sources of harmonics in the power system should be clearly identified, and immediate corrective measures would have to be taken so as to nullify all these problems. Voltage distortion as due to harmonics is generally very harmful because it can enhance the effective peak value and also the RMS current in some devices connected to the network, whereas current distortion causes overheating. In case of capacitor connected to the network, whose impedance would have become drastically decreased as it is inversely proportional to the frequency. See the chart. Source of harmonics, that is non-linear loads, would not have a constant relation of current with voltage and capable of injecting harmonics into an electrical distribution line transformer. 1. Industrial equipments such as arc welding, arc furnace, conduction furnace, variable frequency drives, line switched rectifiers, switch mode power supplies, lighting ballasts, circuits which contain semiconductor power devices such as diodes, thyristors, that is SCRs, transistors, and or switching of loads or circuits. Transformers at no load or low load levels, even they are designed to optimize efficiency around its rated working point. Saturated reactors, static VAR, compensator, HDFC transmission system, solar power conversion. These are all maybe the source of harmonics in the system. Whenever these current waveforms have shown any deviation from the shape of sine wave, then it is understood that they had to contain harmonics. Nature of harmonic frequencies can usually be classified by exhibiting the shape or characteristics of a voltage or current waveform relative to its fundamental frequency. Current harmonics are caused by nonlinear loads, whereas voltage harmonics are mostly caused by current harmonics. Again, I repeat, current harmonics are caused by the nonlinear loads, whereas voltage harmonics are mostly caused by current harmonics. Sinusoidal voltage waveform, as provided by the voltage source, will therefore be distorted by current harmonics due to its source impedance. Harmonic is a component of a wave at a frequency which is the positive integer multiple of the fundamental power line frequency. that is 50 hertz. The even harmonics, whose frequency is a non-zero even integer, that is 2, 4, 6, 8, 10, multiple of the fundamental frequency of the distorted signal, do not normally exist in power system due to symmetry between the positive and negative hubs of a cycle. Hence, the frequency of the even harmonics is the same as the frequency of the fundamental components. The odd harmonics, whose frequency is an odd integer, that is 1, 3, 5, 7, 9, multiple of the fundamental frequency of the distorted signal, of which only integer 1 is the order of the fundamental component. The fundamental waveform can also be described as a first harmonics waveform. However, remaining odd harmonics, whose frequency is an odd integer, that is 3, 5, 7, 9, multiple of the fundamental frequency of the distorted signal, are not the order of the fundamental component. When the transformer which is providing power to non-sinusoidal loads must have to interact a critical phase of Triplen harmonics. Triplen harmonics are therefore be the harmonics whose frequency is an odd integer multiple of the frequency of the third harmonics. As for example, third, 9th, 15th, 21st, etc. Hence, it is concluded that all Triplen harmonics are odd harmonics, but all odd harmonics are not Triplen harmonics. Please note the point. It is concluded that of Triplen harmonics are odd harmonics, but all odd harmonics are not Triplen harmonics. Harmonics are also to be classified by their harmonic sequence. Now, harmonic sequence would have to notify through the phasor rotation of the harmonic voltages of currents with respect to the fundamental waveform of a balanced three-phase four-wire system. Positive sequence of a system of balanced three-phase means that the sine waveform of phase currents or voltages is of 120 degree apart from each other with normal phase rotation RYB, that is 0 degree minus 120 degree, then plus 120 degree. For negative sequence, the sine waveform of phase currents or voltages is of 120 degree apart from each other, but having phase rotation RBY, that is 0 degree, 120 degree, then minus 120 degree. For zero sequence, all are in phase with each other, that is 0 degree, 0 degree, 0 degree, okay? The harmonic phase sequence can be determined by multiplying the harmonic number with the normal sequences of phase rotation in a perfect balanced three-phase system. See the diagram. A, forward rotation, that is positive sequence harmonics of the order 1, 7, 13, harmonic effect, excessive heating. Positive sequence harmonic component would generate a magnetic field which rotates in the same direction as the fundamental, that is forward rotation. B, that is reverse rotation, negative sequence Harmonic component would generate rotating magnetic field in the reverse direction, that is reverse rotation. C. Zero sequence harmonic would not rotate the magnetic field in any direction. There is no rotation. See the diagram. Positive sequence harmonics in order 1, 7, 13, harmonic effect only excessive heating. Negative sequence harmonics of the order 5, 11, 17. Harmonics circulate between the phases, which weakens the motor rotating magnetic flux. Zero sequence Triplen harmonics of the order 3, 9, 15. Therefore, analysis of the sequence components would have to be made by considering three-phase unbalanced system that to be represented as three separate balanced vector systems with equal 120-degree phase relationships. So, if there is an incidence of any degree of unbalanced load conditions in three-phase vector system, then the corresponding phase sequence components may be represented by its three positive, negative, and zero sequence balanced three-phase vector system. Harmonics mainly of the odd orders are usually be the dominant factor, and out of which the fifth and seventh harmonics are the strongest, while the even harmonics are negligibly small. Odd harmonics, which are the odd multiples, that is third, fifth, seventh, etc. of the fundamental, while drawn by the connecting loads, have to instigate the rise of resistance losses as well as eddy current losses in transformers, causing overheating. Even harmonics are the even multiples, that is second, fourth, sixth, etc. of the fundamental, and are fairly small, as because most of the even harmonics created due to have nonlinear loads must tend to cancel each other. There is a sharp distinction between odd, that is symmetrical, and even, that is asymmetrical harmonics. And according to the phase rotation of the fundamental, the basic classification of the harmonics can also be indicated as positive sequence, negative sequence, and zero sequence with their respective order. Harmonics of order 1, 7, 13 are purely positive sequence. Harmonics of order 5, 11, 17 are purely negative sequence. Triplen harmonics of order 3, 9, 15 are purely zero sequence. Positive sequence harmonics would have the phase rotation in the same direction as forward as the fundamental and to circulate between phases. Positive sequence harmonics are rather undesirable as they are responsible for overheating of conductors, power lines, and transformers, which is mainly due to have an addition of the waveforms of the fundamental. Negative sequence harmonics would have the phase rotation in opposite direction, that is reverse direction of the fundamental, and to circulate between phases. Negative sequence harmonics also circulate between the phases, creating additional problems in operational features of the electrical motors, especially induction motors, because due to have the opposite phasor rotation that has forced to weaken the requisite rotating magnetic field of the motors, causing less mechanical torque to produce. Zero sequence harmonics are on phase with the fundamental and circulate between phases and neutral. Zero sequence harmonics are on phase with the fundamental and circulate between phases and neutral. Zero sequence harmonics are composed of triplen harmonics, which are the odd multiples of third harmonic, that is 3, 9, 15, 21. The triplen harmonics are always be a constant threat in terms of efficiency losses, overheating, derating of the motors, generators, transformers, etc., since their ultimate effect on the fundamental waveform are additive. In case of positive and negative sequence harmonics, their current components would have to cancel each other out. Whereas for triplen harmonics, whose current components instead of cancelled out rather add up arithmetically in the common neutral conductor, which is subjected to currents from all three phases. See the effects of triplen harmonics on neutral conductor. Balanced fundamental current components in the neutral are found to be zero, but balanced third harmonic currents would naturally coincide in phase and time. No fundamental current component is in the neutral conductor, but due to presence of third harmonic, the neutral conductor has to contain about 3 times of phase current at 150 Hertz frequency. The resultant effect is thus be the current amplitude in the neutral conductor due to these triplen harmonics could be up to 3 times the amplitude of the phase current at the fundamental frequency, causing the installed equipment to become less efficient. This can be illustrated that if a system has comprised with the presence of fundamental and third harmonic components, then exclusively for fundamental current components, there will be no flow of current through neutral. But for the third harmonic current components, there will be a flow of 3 times the phase currents through the neutral because they naturally coincide in phase and time. Example, in a 50 Hertz installation, if there be a flow of around 10 ampere current for the presence of third order harmonic in each of the 3 phases, then an extra current of around 30 ampere will thereby flow through the neutral conductor at 150 Hertz frequency. So as to withstand these flow of extra current, the neutral conductor will therefore need to be made oversized as compared to the phase conductors. If triplen harmonics are not present, then no fundamental current component flows through the neutral conductor. Comparing the waves of the components of 3 phases with the third harmonic current components and neutral current waveforms. Waveform of a balanced 3-phase fundamental current components with respect to time. Then R phase current with its third harmonic current component with respect to time. Next, yellow phase current with its third harmonic current component with respect to time. Then blue phase current with its third harmonic current component with respect to time. Third harmonic current at RYB are in phase with each other and be additive in neutral conductor. Hence, triplen harmonics would have become an important issue for grounded star connected system, since the line to neutral voltage is theoretically and drastically distorted by the Triplen harmonic voltage drop in the neutral conductor. The Triplen harmonics are of primary concern in case of star-star connected transformers, which are frequently used in substation installations. Ground faults on the transformer secondary side are immediately be imposed as ground faults on the primary, since the zero sequence current components would directly pass through the transformer, making the relay protection difficult. However, in case of delta star transformer, the ground faults on transformer secondary do not cause zero sequence current to flow in the transformer primary circuit. In some high rating star-star connected transformer, an additional window, that is additional winding, is provided apart from primary and secondary windings. Again, I repeat, in some high rating star-star connected transformer, an additional winding is provided apart from primary and secondary windings. This additional third winding is usually termed as tertiary winding, which is rather typically of delta connected winding and provides a path for zero sequence currents during short circuit and ultimately suppress Triplen harmonic currents. Relevant application problem in star-star connected power transformers. Star-star connected transformer, while connected to the power system, would have usually been loaded with continuous or transient unbalanced loads, and for which current will flow through the secondary neutral. Because of this flow of current and having with zero sequence impedance of the transformer, there will be a zero sequence voltage drop. For balanced load, normal value of the neutral voltage with respect to ground is 0. But this zero sequence voltage drop has then to be responsible for enhancing the neutral voltage other than 0. For ungrounded neutral and under unbalanced loads, the sum of the voltages at the neutral points is no longer 0 with respect to ground, and that leads to shifting of neutral. Greater be the load unbalancing, more will be the neutral shift. For continuous or transient unbalanced loading, the zero sequence current magnitudes, though might have been in lower level, but in case of unbalanced faults like single line to ground fault, these zero sequence current magnitudes would have become rather high enough to cause abnormal heating effects in the transformer. This has happened as because such type of unbalanced faults may have also to create a very high extent of neutral shift. Even the secondary neutral is grounded, but having with a high zero sequence impedance of the system or of the transformer, then also might have been a chance of causing significant neutral shift. Therefore, transformers without having neutral connection or not have a provision of stabilizing winding are not feasible to supply significant unbalanced loads for longer duration or high short circuit currents for shorter duration. Interference drawn regarding unbalanced loading of star-star connection. Without having neutral connection while an unbalanced load is connected, then the phase voltages would have become severely unbalanced. Transformer magnetizing current is thereby tend to be in non-sinusoidal waveform and be comprised of third harmonic current component. In an ungrounded star connection, there would have been no path for these harmonics in magnetizing currents. These harmonic current components intend to distort the magnetic flux wave, which therefore will induce a voltage having a third harmonic component in each of the windings, both or primary and secondary sides. This third harmonic component of the induced voltage may be as large as the fundamental voltage. When this induced voltage is added to the fundamental voltage, then the maximum voltage is about 2 times of the normal voltage. Again, I repeat, when this induced voltage is added to the fundamental voltage, then the maximum voltage is about 2 times of the normal voltage. Solution for unbalanced loading and third harmonic problem. For large transformer like generator transformer, if there is any unbalancing of load on transformer secondary side, then the phase voltages of primary side of the transformer would have also become severely unbalanced unless its Y point is earth. Magnetizing current as drawn by the primary windings has compiled with third harmonics whose current component of each phase will be in phase with each other. These current components would never be cancelled out each other, rather be added in phase with one another to produce a significant amount of zero sequence neutral current if a path is established for the neutral current to flow. In case the primary side star point is not connected to neutral point of the generator for having with isolated neutral, then third harmonic current components of each phase cannot have return path to flow. Again, I repeat, in case the primary side star point is not connected to neutral point of the generator or having with isolated neutral, then third harmonic current components of each phase cannot have a return path to flow. Hence, the magnetic flux in transformer core would never be of a sinusoidal type and the voltages will be rather distorted. However, shifting of neutral point can be avoided by connecting the primary star point of the transformer to the neutral point of the generator. However, shifting of neutral point can be avoided by connecting the primary star point of the transformer to the neutral point of the generator. A solid connection of the two neutral points would have to provide a low impedance path, which therefore allows the third harmonic currents to flow in the neutral instead of inducing large voltages. Neutral wire is also made a provision of a return path for the unbalanced currents caused by the unbalanced loads. However, the triplen frequency currents in the neutral wire may interfere with the nearby telephone lines and other communication circuits. when no way to provide neutral in a star-star connected transformer. In some high rating star-star connected transformer, an additional delta connected auxiliary winding is provided apart from primary and secondary windings. This additional delta connected auxiliary winding is termed as tertiary winding. Usually, when the tertiary winding is used for the protection of the transformer, then this tertiary winding is termed as stabilizing winding. Again, I repeat, usually when the tertiary winding is used for the protection of the transformer, then this tertiary winding is termed as stabilizing winding. When the tertiary winding is used to cater some small load with the transformers, then it is termed as auxiliary winding. It is therefore employed for supplying to some auxiliaries at different voltage levels from the primary and secondary windings. While tertiary winding is used as stabilizing winding, particularly in star-star connected three-phase transformers, then it may serve for the following purpose. One, it helps to stabilize the neutral point of the fundamental frequency voltages. Line to line voltages would remain same, but due to third harmonic components, the phase voltages in individual phases are varying drastically. This can happen if star neutral is ungrounded. To minimize third harmonic voltage and the resultant effects on the system, over voltages can develop with resonance between zero sequence capacitance of primary or secondary system and transformer third harmonic inductance. To minimize the residual direct current, DC, magnetomotive force, that is residual magnetism in the core. It can minimize the residual direct current magnetomotive force, that is residual magnetism in the core. Number 4, placement of buried tertiary winding, that is stabilizing winding, in star-star connected transformer would have an effect to reduce the zero sequence impedance of the transformer, as well as to limit the generation and flow of third harmonic voltage and currents. To reduce losses from zero sequence fluxes impinging on tank and other metal parts. Again, I repeat, to reduce losses from zero sequence fluxes which is impinging on tank and other metal parts. As the tertiary winding is connected in delta formation in 3-winding transformer, it assists to limit fault current in the event of a short circuit from the line to ground. In star-star connection, an unbalanced load may have a result in neutral displacement, and third harmonic currents may circulate between lines and earth. All these problems can be neutralized by providing delta connected stabilizing or tertiary winding with a rating sufficient to take short circuit fault currents. So during designing the stabilizing winding, you have to judge the short circuit fault currents. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.